stuff going for 6162? How's our calculus stuff going here? Do you want to start with some questions from homeworks? We can do some of that. Back. 6-2, number 11. Certainly. Is that, yeah, that's that one. It's a good one. Okay, so I'm going to start by looking for my stylus. There it is. We'll get a picture first, right? Since we need a picture of that two-dimensional space really to proceed at all. So let's try to do that. So if I'm going to plot points to graph y equals x squared, what kind of function is y equals x squared? Quadratic, right? Yeah, it looks like a parabola. What points do I need to graph a parabola? I need the vertex, and then 1 point on either side should be sufficient, right? What's the vertex going to be for y equals x squared? 0, 0, right? Everybody should kind of know that inherently. That should be an Algebra 2 fact we remember. In general, how do we find the vertex for a quadratic? Negative b over 2a is the formula to find the x-coordinate for the vertex for any quadratic. Again, would the AP expect you to remember that? Probably, yeah, probably. I know. The good news is that it would likely come in a calculator active section where you memorizing that is less important because your calculator can find it for you in the worst case scenario. All right. And then we have x equals y squared. So again, this is going to be quadratic, but it's in terms of like y is the independent variable, or y is the dependent variable. No, y is the independent variable and x is the dependent variable, right? It's like going to be kind of flippy-floppied. The vertex still should be the same though, right? Now what we're going to do is we're going to pick a value for y and find the corresponding value for x. So let's just pick -1 for y. When I square -1, I get +1 for x. And I'll pick +1 for y. When I square that, I get +1 for x. So if I plot this, so I'll do there's that. There's that. So this is like my shaded region. Does everybody feel okay there? I can zoom out or whatever if we're having trouble. It looks like Giselle's playing head bob with Lorenzo. You can scoot to the side or something if you need to, like, just give yourself like 6 inches one way or the other. Like, I get it.
Yeah, much better.
Yeah. And then we're going to be rotating about the line y equals 1. So we're going to be kind of doing that. All right. So what is this shape going to look like? With a three-dimensional shape for this. Try to do that a little bit better. So it's kind of like a funnel that doesn't have an opening at the bottom. It comes to a point. But instead of a funnel being like smooth straight in, it's going to be kind of like curved. So it's kind of like a gumdrop with a Hershey Kiss pulled out of the middle. Is that, you vaguely kind of see what I'm saying there? I'm going to try to, whenever possible, like try to describe it in a stupid way that's like, oh, I know what those shapes look like. I can kind of imagine that a little bit better because my picture is rough, right? Hard to see what's going on there. The key is recognizing that there's going to be an opening in the middle, right? This is a concave surface. Can we all see that at least? And usually it's easy to see because you have like some open space between the curve and your axis of rotation, right? So here's the line, y equals 1. And then we're going to have like, red curve on the outside and like blue curve on the inside. Everybody okay with that idea? All right. So I know we're going to be integrating with respect to which variable? Which way are we slicing? I'm going to be slicing vertically, right? Everybody agree? So that my cross sections are all those donuts. We're perpendicular to the x-axis. That means we're integrating with respect to x. Everybody's okay with that idea? So my area function is also going to be with respect to x. So to find the area of that donut, it's going to be pi r outer squared minus pi r inner squared. And then we'll be integrating after we have that from 0 to 1 a of x dx, right? So it just comes down to now figuring out what this r outer of x and r inner of x, how do we write that? Does everybody feel okay so far? All right. So let's go look at our picture here. So this would be like my r outer, right? Again, I'm going from the axis of rotation to the outermost part of my function. So if that's just some point xy, what is that distance right there? That's y, right? The y coordinate for that point xy.
Full thing or just like
just the little bottom here, right? Just that little squiggle. And how far is that whole distance? 1. So what is r outer? 1 minus y, right? If we want just that part, that's 1 minus y. Can everybody kind of see how we came up with that? Rita.
Why did you like the little part y?
Because to plot that point, I go x over and then y up, right? Does that make sense? So it's just strictly because that's how we plot points. Oftentimes, the trickiest piece to remember is like, oh, yeah, that's just the x or the y for that point or whatever, but that's the idea. All right, so we have r outer is equal to 1 minus y, right? But we don't want r outer in terms of y because we're integrating with respect to x. The good news is that this y I know is just equal to x squared, right? Because it's a point on that red curve. Anything on that red curve, any point on that red curve is x comma x squared, right? Will it always? Well, I'm going to say always no, but oftentimes yes. Because we're going to see an example here leading us into the next section about a case where this method of like taking cross sections and building little cylinders isn't really going to work for us. So I can't say always. Is that fair? Okay. Now let's do the same thing with our inner, right? So that's our R inner. Everybody feel okay there? So again, what is that distance there? I drew the squiggle. It's y. What is this distance here? 1. So our inner is 1 minus y again, right? Now we have a little bit of extra work to do this time because the y here, I have to do a little bit of work. What is y going to be, though, if x is equal to y squared? The square root of x, right? Now, technically speaking, it should be plus or minus. How do I know that I can drop the minus? Because I'm on the plus part of my parabola, right? Can everybody see that? The point that I'm drawing is on that plus part, so I can drop the minus. And now we got everything we need. So our volume integral from 0 to 1 of pi r outer squared minus r inner squared dx. Is everybody okay that I factor that pi? All right, to integrate this, what should I do? What? Yeah, I would FOIL that out, right? You could like do some rearranging and do some U sub, but I wouldn't bother with it. The FOIL is pretty easy. So we're going to have 1 minus 2x squared plus x to the 4th minus 1 plus x minus, oops. That's not x. That's minus or plus square root x, oops, 2 square root x's, and then minus x dx. Okay. Yeah, that looks good. I noticed that the -1 and +1 can combine to give us 0. Let's go ahead and do that simplification. But other than that, I don't see anything else simplifying to do. So we're ready to do our antiderivative. The antiderivative of x squared. Antiderivative of x to the 4th. Antiderivative of x to the 1/2. And antiderivative of x so if I plug in 1, I'm going to get -2/3 plus 1/5 plus 4/3 minus 1/2, and then plus 0 minus 0 minus 0 plus 0. If I make a common denominator, looks like that's 30. So -20 over 30 plus 6 over 30 plus 40 over 30 minus 15 over 30. So let's see, that's now to 20, and then that brings that down to 5, and then plus 6 more. So that gives me 11 pi over 30. I think that's the right answer. Does that feel okay back? Sure, Rita.
Sorry, Bex, or about like the inner, how did you get the square root of x?
So I found that r inner was 1 minus y, right? If I go to the equation for the inner function, that's x equals y squared. So to figure out y in terms of x, I just square rooted both sides. So y is going to be plus or minus the square root of x. And I decided that I needed the positive square root because I'm on the positive part of the parabola, the part that's above the x-axis. Sure. Does that feel okay on what we did there? So number one thing here, doing a good job with this picture really is helpful, right? Don't try to draw a tiny picture, draw it big. Even the picture I drew is probably a little smaller than I probably should have because it got a little cramped in there. But draw a nice, neat, good picture. This is typically all we'll really need to do a good job on these. The other pictures will become less and less important the better you get at this, where it's like, this is what I really want to look at. But to build out your intuition of like knowing what variable we're integrating with respect to, what does the cross section look like, doing those other parts helps a lot. Because until we get a little bit of intuition, get some experience looking at this, I don't know if you'd be able to tell what variable you should be integrating with, what cross section is going to look like. That's going to take some experience, but not too much. Beck.
So when the cross sections are vertical, you integrate with respect to x?
Mm-hmm. So the way I think about it is if I'm slicing, the axis that I'm perpendicular to, that's the axis I'm integrating with respect to. So if I'm slicing vertically, that's perpendicular to x, I integrate with respect to x. If I'm slicing horizontally, that's perpendicular to y, I want to integrate with respect to y.
Okay,
Yeah, in general, that rule's pretty hard and fast. At least for doing the slicing. We're going to see a different method of doing this today where I think the rule is reversed. Giselle.
Number 13, can you just draw like
The picture?
picture of just the shape? Yeah.
Sure.
I get the graph of it, but I don't like
Oh, the three-dimensional picture?
Yeah, the three-dimensional.
Yeah, well, let's get up to that point. So, because I'm going to use the one to get the other, right? So let's just kind of redo that process together. Oh boy, that put it somewhere I didn't expect it. All right. All right, so secant. Remembers what we're going to need to graph that guy. It has asymptotes. Where are the asymptotes going to be? When cosine is equal to 0. When is cosine equal to 0? At 90 degrees, so pi over 2. And every pi after that, right? Those are my asymptotes. I guess I should probably need some on both sides here. So let's just say pi over 4, we'll call this one pi over 2. Actually, let's give ourselves a little bit more space than maybe I thought we would need. So let's say that's negative pi over 2, 2, 3, 4. And let's make this one positive pi over 2. Okay. Everybody feel good so far with the placement for our asymptotes? So if we're just making like an XY table, I would do these values. Because I know pi over 4, right? What's cosine of pi over 4? Square root of 2 over 2. But this is secant, so we're going to reciprocal it. What's the reciprocal of square root 2 over 2? How about just square root 2? Right? If I have square root 2 over 2, if I reciprocal that, that's like to the 1, that's like the 1/2, right? You guys can see that. And then we have plus 1 though, right? Because our function is 1 plus secant of x. So that is about 2.4. Square root of 2 is about 1.4. What's cosine of negative pi over 4? It's not negative. Remember, all silly turtles crawl? Cosine is positive in the fourth quadrant also. So also that. And what's cosine of 0? 1. So 1 plus 1 is 2. So far, so good. All right. Let's make this the line y equals 1 here. So we're going to have, that would be, oops, let's use black. That's like negative pi over 4. That's like positive pi over 4. So we have like, so this is like 2, this would be like 2.4, that'll be like 2.4. So it'll be like that. Everybody feel okay on the picture? Oh, shoot. I put the wrong line. Mr. Kulik, what are you doing here? I wrote in the line y equals 1 like that was the boundary. That's not the boundary, you dumbo. What's the boundary at? Y equals 3. If I would have noticed that, I would have left myself a lot more space. So like that's my guy there, right? Something like that. And then we're rotating about this guy. So, Giselle's question was, I'm having trouble picturing what that's going to look like. This is kind of what, or how Mr. Kulik thinks about this in his head. Grab an obnoxious color here. So I'm going to think about it. I'm going to make like a circle at each one of these ends, right? Since that distance is like the radius. Does that feel okay? Because we're rotating about. And then I would get the same kind of circle here. So like, does that feel okay there?
How is there no circle? Oh, because there's a
Because
gap. There's a
everything,
gap.
yes, yeah, everything is rotating, right? So like, you can get like one of those. So the way I'm going to picture this now then is this is like straight across, and like in the middle, it's kind of doing one of these. So I have like a cylinder with like a funnel kind of through the middle, right? Like two funnels kind of merged together inside of a cylinder. Did any of you guys have like that thing when you were growing up where you took like, it was like a little attachment, you screwed like two 2-liters together and you put water in them and like you flipped it over and made like a tornado in the water? You saw one of these things before, right? At some point. That's what the inside of that thing looks like, is basically that. I don't know. I'm trying, guys. Yeah, it's kind of like an hourglass shape. Yes, great. Perfect description. Does that feel okay, Giselle?
Mm-hmm.
And that's the part you wanted, right? Was like, how am I trying to picture that?
Could you do like the yeah.
Oh, keep going with the problem.
Yeah.
Yes. Oh, sorry.
Thank you.
Yeah, no problem. Okay. So, shape here of the cross section, clearly discs or washers, right? Like we can see that easily because, well, there's a gap in between the shaded area and the axis of rotation, right? Anytime I have any gap there, that's going to be the case. So I have an R inner and an R outer. Let's just use this one. So let's say here, that would be like my inner radius, right? Since it's going from the axis of rotation to the nearest edge of my shaded area, right? Or the boundary of my shaded area. Everybody agree? How far is that distance then here? that's 1, right? Because that's the line y equals 1. I gave 2 units of space just so I could spread this out and give myself a little bit of space to work in. And how far is that distance? That's y, right? That's just the y coordinate. This is the point x comma y. So what is our inner going to be? Y minus 1. Everybody agree? And what is y in this case? Is 1 plus secant x. So there's that. Is everybody okay? Giselle, you feel all right?
Yeah.
All right. Here's the lovely part. If I look at the R outer, that's that distance, right? Regardless of the x that I pick, R outer is constant, isn't it? It's always that distance from the line y equals 1 to the line y equals 3. Guess what R outer is then? Just 2. Because no matter where I draw that R outer, it's the same distance, right? R outer is going from our axis of rotation to the end of our shaded region. No matter where I draw R outer, whether I draw it here, or if I draw it over here, it's the same distance, right? It's the same length. It's a constant, which is awesome. I love that. Rita.
So our inner is always like from like the shaded part to that axis, and then our outer is like from the.
Here's what I think about it. Our inner would be from the axis of rotation to the start of the shaded region.
That's inner.
Inner. Outer would be from axis of rotation to the end of the shaded region. Okay. Giselle, happy? Okay. So our volume then is the integral from negative pi over 2 to positive pi over 2 of pi times r outer squared minus r inner squared. Well, I'm just going to just write it this way. Dx. So far, so good. Now I'm going to make a observation here. Look at the graph of secant, or look at the graph of the shaded region. What type of function is that blue graph? It is even function because it's symmetric about the y-axis, right? So you know what I'm going to do? I'm going to just, instead of going from the integral from negative pi over 2 to positive pi over 2, I'm going to do 2 times the integral from 0 to pi over 2. That'll make life a little bit simpler when I go to plug stuff in later. What is the antiderivative of negative secant squared? Negative tangent. Remember those derivative rules that I asked you to memorize and told you that they weren't going to go away and that you should really want to make sure you do a good job memorizing those? They don't go away. You have to have them. Yes, Katie.
Is the rule like when you multiply by the 2 pi? Is that just like?
So the rule was if f of x is even, the integral from negative a to positive a of f of x dx equals 2 times the integral from 0 to a f of x dx.
Oh, the pi just came on the inside.
The pi was, yes, that pi was from, is that pi. Does that feel good? Okay. Yeah, no problem. So we have 2 pi times, well, when I plug pi over 2 into 4 pi, I get 2 pi again. And tangent of pi over 2 is 1, right, Katie?
How do you tell if it's like just like the equation?
I didn't do it on the equation. I used the graph. So because the graph of y equals secant plus 1 was symmetric about the y-axis.
Can you do it based on the equation?
You could if you had it memorized that cosine was an even function. But probably I'm looking at the picture, to be honest with you. Like more often than not, that's how I would be doing it. Especially with the trig stuff. Sine and cosine and tangent, I probably remember what they are. But I wouldn't trust myself and I'd be like, I'm drawing the picture anyways. I'll just look at the picture. Okay. And then when I plug 0 in, minus 0 plus 0. So I think I get 4 pi squared minus 2 pi. Let's check the answers on that. That's a weird answer, but it might be right. Which one was this? 13, Giselle?
Yeah.
Is that what we're doing? Oh. So we did everything good. Here's the issue. Okay. Here's the issue. You ready to, everybody watching? I did make a small mistake here. This should have been where we stopped, right? Because this guy continues going like past 3. Right, because we have the dashed line as y equals 3. So we integrated too much stuff. Oh no! So let's figure out what that was. So we need y equals 1 plus secant x. We need that to equal 3, right? Everybody feel okay? So to solve this, I'm going to subtract 1 from both sides. I'm a lot better on the unit circle with cosine than with secant. I think you guys would probably agree with that. So what we'll do is we'll do the reciprocal of both sides. And then where on the unit circle is cosine equal to 1/2? So again, I think about the picture on this. So cosine is x. X is equal to 1/2 like here. So we're looking at that angle. Pi over 6 would be like that angle. So we're pi over 3 is the one we want, right? Want the one where the x is short, so that means we have a big angle. So we'll just fix that real quick. So we go down here, there's not so much to fix. Just Just change those to 3s. Change that to a 3. And now we have 4 pi over 3. And then tangent of pi over 3 is so it's sine of, which is 1/2, or I'm sorry, is root 3 over 2, and cosine was 1/2, or that just simplifies down to root 3. So we'll just call this then 2 pi times 4 pi over 3 minus root 3. We'll just stop there. No algebra mistake, but I made a setup mistake because I just figured, oh yeah, I didn't think about it. I drew the picture and I drew it right. And it's like, integrate from negative pi to positive pi, 2 pi, or negative pi over 2 to positive pi over 2. Don't even mind that it doesn't go all the way, and then like clearly it's cut off. I drew it the right way in the picture. Tessa. Uh-huh. You're welcome. All right. So let's look at, as I've hinted at, situations where this method that we've been using of like building these little cylinders using cross-sectional area, where that's going to get us into trouble, where that's going to fail. Cool? All right. So let's say we have this problem. Let's say we wanted to find the volume of the solid obtained by rotating the y-axis, the region bounded by y equals 2x squared minus x cubed and y equals 0. So basically we have this shaded region, right? So if we do that using the same thing, or the same idea, what the heck happened? How did I do that? I don't even know. That's like our R inner. And that would be like our R outer, right? Everybody kind of see that? What's the issue we're going to run into? Nope, that's not the issue. It's a very simple thing, but it's a very big issue for us in setting up the problem the way we just did.
R outer minus R inner.
Well, what function is R inner?
X.
It's y equals 2x squared minus x cubed, right? And what function is R outer? Also the same function. How do I differentiate when R inner needs to be the first point on that for that specific y value, and then R outer needs to be the second x point for that specific y value? Right? Like there's not a clear way to kind of differentiate that, because they're both just like using the same function. So what do? We would somehow, if we wanted to continue using that same method, be able to rewrite that function as a function of x in terms of y. I can't do that without looking up the general form for a cubic equation. No one's going to expect you to look up the general form for a cubic equation. We're just not going to do it that way. Okay? Instead, what we're going to be doing is using, instead of like cylinders of infinitely small height, like slicing the thing up into cylinders of all infinitely small height, instead what we're going to be doing is like skinning it with cylinders of infinitely thin thickness. So we're just going to kind of like peel it like an apple. And every time we peel, that skin will calculate the volume of that skin that we just peeled, and then peel it again. And we'll do that for infinitely many thin peels, and then add up the volume of each peel, each time we do a peel. Does that kind of make sense? Okay. So, in general, the volume of one of these hollow cylinders, one of these shells, which is kind of what we call this is the shell method, is going to be the perimeter times the height times the thickness. Okay? So it's the circumference of our shell times the height of our shell times the thickness, how thick that shell is, right? So like the delta R is our thickness. Okay. So say we have something like this. That's our three-dimensional shape, right? That's drawn next to us. What we're doing is we're going to be building these cylinders. So like each one of these is an example of a cylinder. Everybody's okay? Now the thicknesses are quite big here, right? As they've drawn. As we make those thicknesses of the cylinders thinner and thinner and thinner, we see that we're going to be approximating the shape that we had before. You guys kind of see the idea? Intuitively, this one is, I think, more difficult to see, less natural. But it's kind of like, like a Russian nesting doll kind of thing, right? Where you're just like, you start with the inside and you like keep stacking another layer on top of it till you get like the whole thing, kind of. But you can see that we can do this all with cylinders, right? Notice that, me personally, would I ever choose to use this method if there's not a hole or a concavity inside my shape? No, man. Only going to do it if I have like a concave shape or a shape with a hole in it. If it's solid all the way through, I would not bother to do this. Disc me up, man. I'll take that. That's easy. All right. So in general, our formula then becomes 2 pi times x times f of x dx where we're integrating again from a to b. So let's work through some examples here to get the feel for this setup-wise, right? Yes, Beck?
Is the x in that equation the thickness of the cylinders?
The dx is still the thickness. The x is like the height of the cylinder. Oh no, I'm sorry. So this 2 pi x is the circumference. The height of the cylinder is the f of x. And the dx is like the thickness. Mm-hmm. Okay. So let's go back to this motivating problem, the one that we saw that was going to be a big issue trying to use our washer to do. And let's attack this now with these cylindrical shells. Bless you. So I snagged this picture from the book because I think this really helps like understand the setup. So at any value x, the height of that cylinder is going to be the y coordinate, which is just our function, right? You guys can see that? Now, the only hiccup here is, what are we integrating this by? From what to what? Where does my cylinder, or what x value is going to be the smallest possible cylinder? Be like right there, right? That'll be a cylinder basically with radius 0. And what x value is going to be the biggest possible cylinder? Out here, right? That's basically a cylinder with 0 height, but it's like super wide. So that's my plan. Look at how wonderful that is to set up. It was like almost nothing to do. I didn't have to like visualize this too bad at all, right? So what are we going to do to integrate this? Yeah.
We just get that two from the graph.
The top two?
Yeah.
Yeah. So basically what I did, Elaine, is I looked at the cylinders that I'd be making, the cylindrical shells, and I asked, like, what's the widest cylinder I would want? And it would be like that one that'd be like super short but really wide. So that's the 2. And what's the smallest, the least wide cylinder I'd want to make? Well, that's starting here at 0, right?
Do you always have a picture?
No.
Will we ever have a picture?
Yeah.
If he ever.
Depends on the question. Could be a calculator problem. Likely would be a calculator problem, in which case you can supply your own picture with your calculator, usually, without a whole lot of problem. So to integrate this, what are we going to have to do? Yeah, I would distribute the x through, right? And I'll pull the 2 pi out front. So that's going to be 2x to the 4th over 4 minus x to the 5th over 5 from 0 to 2. So we have 2 pi. And then we're going to have 2 to the 4th over 2. Like I reduced those, right? Minus 2 to the 5th over 5 minus 0 plus 0. So let's see, what do I get? 2 to the 4th is 16, divided by 2 is 8. 2 to the 5th is 32. So I got to make that, they have a common denominator, make that 8 into 40 over 5. So we end up with 8 over 5 times 2 pi would be 16 pi over 5. again, so let's do another. Notice here this problem is a little different because we're rotating about the x-axis now instead of the y. Definitely will not. That's the third piece of this two-paired lesson is to like, now I'm going to give you problems where you have to decide which one you want to do.
And this one only works with like whole.
No. I would say you would only want to use it if there's like a concavity through or a hole in your figure. You could use it for a solid, but like the setup actually becomes I think harder than just the disc, which is like super straightforward. I don't know if that helps you at all. Yeah, I know.
Yeah. Okay. No, yeah, looking back, the solid, the other one.
Yeah. In general, like, there's that. That's okay. All right. So notice here, we're asked to use cylindrical shells to find the volume of the solid by rotating about the x-axis, the region under the curve, y equals square root of x, from 0 to 1. Notice in the previous problem, when we rotated about the y-axis, we integrated with respect to x. Here we're rotating about the x-axis. We're going to be integrating with respect to y. Oops, volume equals. Everybody's okay with that? So it's going to be a y that we're integrating with. So again, my cylinders are going to be like, I don't want to draw this. Okay, so for some y value, right, this is like that's like my radius, that's like the 2 pi r. That's just y, hence the y there. This is going to be the height. Always through the shaded region is the height. So I know that this, so this distance here is x, right? So we go x over and y up. And I know that this distance is 1. So what is that height have to be 1 minus x. But x in this case is going to come from a point on that function. I need that x in terms of y's. So if I square both sides, y squared is equal to x, right? And then we're going to be integrating starting at y equals 0 out to y equals 1. And we're done. We just got to grind through the calculus. Does that feel okay? I have. Are we still writing on this? I don't want to move it if people are still writing. Okay. Katie.
Why do I know you have to subtract that x from the? I feel like we did in the last one, we just used it.
So if I look here, as we're picking some x, that's like the radius, and that's like the height, right? Well, that point is just x comma y or x comma whatever. So because we're going through the shaded region, the height is just the y value, right? Here, though, if I look, the height of my cylinders is coming this side instead of this side. You get what I'm saying?
Yeah, how is it the height in the first one? Then? Isn't it like a straight line? How is that?
Well, the height is going to be different depending on the width of your cylinder, right? So if my x is over here now that's my height, right? The height is variable. Does that make sense? So yes, the height is like a number, but it's a different number depending on how wide your cylinder is. Is that?
And the second one, the height is like 4.
So the height of your, so like, if we think about it, you're getting like one of these things, right? So when I build out my cylinder, you know, like, so like my height is always going to be going this direction, right? And then maybe my next cylinder is like here. You get what I'm saying? So again, the height is variable, right? Does that help?
You just like chose x as a variable.
I chose x as a variable.
Like when you were subtracting.
For which problem?
For this one.
This one, okay.
When you were just trying to find what's the point.
So what I said is that this point here is like x comma y, right?
Yeah.
So like literally that's the x coordinate and that's the y coordinate. Now the y coordinate is representing the radius of my cylinder that I'm building to kind of my shell, I should say. Is that, you see that now?
Yeah.
Okay, sure. All right, let's try doing one more. Okay, it says find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared, y equals 0, about the line x equals 2. So That's my shaded region, right? There's my line, x equals 2, right? Okay. Which one is this going to be more similar to, the first one or the second one? The first one, because we're rotating about, I'm sorry. Yeah, the first one, because we're rotating, no. Y equals 0, x equals x-axis. About the y-axis. Yeah, so that's going to be more similar to the first one, where we're rotating about a vertical axis, right? Sorry. So we're going to be doing that. Does that feel okay? So if I pick some x here, that's like the radius for my cylinder. The height of my cylinder then is going to go through the shaded region. That'll be my height, correct? Okay. But here's the catch here. I should say this is like an X. But what's the radius really for my cylinder supposed to be? Where's my axis of rotation? That's really my radius, right? Because the radius is always from the axis of rotation. So that radius should be 2 minus x, because we know this distance is 2.
Why do you include X? Like, why-
Okay, you said it twice, and I was a little bit quiet, and maybe your hand was over. I didn't quite understand.
Why do you like subtract X?
Okay. So the radius of my cylinder, the cylinders that I'm building, have to be centered at the axis of rotation, right?
Okay.
So like my first cylinder is going to look like that. That's going to be like the circle part for it.
Oh, so you just stop it.
So the radius has to, whatever that outer point is going to be like the end of my radius, right?
Yeah. And you can just choose whatever.
And then the height is going to happen at whatever that end of that radius is.
You just like choose whatever you want.
I'm just kind of drawing an arbitrary shell so that I can name the things with proper. Does that make sense?
Yeah.
So yes, in a way, you can just pick that to look however you want, anywhere you want it to end. But yes, that's the idea. Does that feel okay?
Yeah.
Did I answer your question?
Yeah.
Okay. Okay. So our radius then is 2 minus x. Our height is just the function. What are we integrating from? Well, if my radius, what is the minimum this could be? 1, right? What's the biggest that could be? 2, right? So what x value gives me the minimum? 1, right? If x is 1, then I have a radius of 1. And what x value gives me the, and what value x value gives me the biggest? 0, because when x is 0, the radius is 2, right? Remember, this is the radius here. Remember, that piece is the radius. If we said the biggest it can be is 1, or sorry, the biggest it can be is 2 and the smallest it can be is 1, then x has to go from 0 to 1.
Why is this supposed to be as one?
Well, because there's no more shading, right? Like when I draw this figure of rotation, there's that, like the biggest empty space. If it's smaller than 1, you're like have a cylinder with you're not counting any of the shaded, you know what I mean? Like 2 the shaded is the smallest it can be. Is that, that was a terrible vocabulary from me. So you have like this thing, right? And it's like it's like this, but it's like sloping down into it. Right? So it's kind of like a wedge shape or whatever. Or like think about a stadium, right? A stadium's like a cylinder and then it like slopes down in. It's kind of like that shape. So like that's like my 1, like just to the bottom of the stadium. Couldn't be any less than that because I'd be like trying to count air. I don't want to count air, I want to count the stadium. Does that make?
Yeah, that makes sense.
Okay. Like getting a 3-dimensional picture in your head is hard, especially on some, like this one's a tricky one. All right. So for right now, I just want you to work on these ones. Okay. Eventually we're going to do the part 2 one, but we'll do that in class with a partner as a dedicated day. Part 2 is pick the method. And if it makes life easier here, like just do the setup and like you can handle the integration on your calculator. And if it saves you the time on these problems, get the setup done by hand and then just have your calculator integrated to make sure the setup is correct, that you're getting the same answers at the back of the book, and then go on about your day. Does that sound okay? Save yourself some arithmeticking.
Did you say we have a test next?
Well, I have 2 more sections still that we want to talk about. We'll take another day this week to do volumes. So not next week.
When we get back on, right? Probably.
Yeah, it'll probably, I don't want to cram. No, do you want to do it before break?
No, I don't know about that.
Okay, that's fine. Everybody looked upset anything was being said, so I just wanted to double check.